Hey, physical science classes. In this video, we're going to look at some of the basic notes about projectiles that we're studying this week. This is relevant for our classes from September 28th to October 2nd. For those of you coming to school in class, we'll be doing a lab in class about the acceleration due to gravity. If you're 100% virtual, there is a virtual simulation lab that's new for this week, which is actually about projectiles, and you'll complete that. You'll see the assignment in your assignments tab if you are a 100% virtual student for right now. In the notes here, we have in our content library, motion notes number 3, we start off just as this definition of what projectiles are. So a good comparison to make is that first we had objects moving just horizontally at a constant speed. Then the next week about motion, we talked about objects that are falling from rest and speeding up because gravity is accelerating them. And we know that the acceleration that these objects experience when they're falling is this special acceleration called the acceleration due to gravity, or little g. And we symbolize that with just the lowercase g, and that's the acceleration due to gravity. And that's what you'll be finding when you do your lab in class, if you're here in class this week with us. That value for little g, the acceleration due to gravity, is 9.8 meters per second squared, or we round to 10 meters per second squared if we're just solving a problem. So the 9.8 is what we use in labs. This is the so-called actual value. And 10 meters per second is what you're allowed to round it to when you're doing a problem or an assessment question. That's just for problems. And we went over how that means 10 meters per second squared means 10 meters per second. So if I drop an object after 1 second of falling, being dropped from rest, after 1 second of falling, it's moving at 10 meters per second. After 2 seconds of falling from rest, it'll be moving at 20 meters per second. After 3 seconds, it'll be moving at 30 meters per second. So at every second, it's increasing its speed by this constant amount of 10 meters per second every second. And that's what that value for the acceleration due to gravity means. If I throw something upwards at a certain speed, after 1 second, it's going to be traveling upwards 10 meters per second slower, because gravitational acceleration is always pointing down towards the center of the Earth or towards the ground. So that was the first 2 weeks of motion stuff that we looked at. We had a speed equation that we could use for something traveling at a constant speed horizontally. We have the free fall equation if we have something dropped from rest and it's falling and speeding up. Those are two of the math equations we have available. With projectiles, we have something that's traveling through space, usually in a curved arc, and it's moving in both the horizontal direction and it's moving in the vertical direction at the same time. So projectiles are an example of a type of motion where something's moving in both directions, horizontal and vertical, at the same time. We're only going to look at one type of possible projectiles this week, which will be exactly what our assessment question is about. And that type of projectile is a projectile that is launched or shot horizontally, like off the edge of the table, or if you mounted a Nerf gun launcher and it shot something perfectly horizontally, that's the type of projectile we're looking at. There are lots of other different examples, as you can see in the notes here, of what a projectile could be. We're assuming that there's no air resistance. That's very important. Because there's no air resistance, that means free fall applies to our projectiles. We'll have free fall in the vertical or the y direction, Sometimes these horizontally launched projectiles, again, the only type we're looking at in our class, I'll abbreviate HLP, so that stands for horizontally launched projectile. We'll see some examples of it there. Baseline stuff for all of our projectiles, we still have the same two principles, either constant velocity motion, CVM, or uniformly accelerated motion, UAM. And because we have projectiles that are traveling in both the horizontal and the vertical directions at the same time, we get to say that both principles apply. The constant velocity motion principle applies in the horizontal direction of the projectile's motion, the uniformly accelerated motion and free fall apply in the vertical direction. Free fall only applies in the vertical direction because that's the direction gravity and the gravitational acceleration are pointing in. This video you need to watch. Open it up in a separate tab. You can get to it from our content library, motion notes number 3. This is showing two billiard balls, one being shot horizontally by a piston that shoots out, and at the exact same time that first ball is shot out horizontally, another ball begins to fall just vertically from rest. And you'll notice in the video they hit the ground at the exact same time. So our projectiles that are launched horizontally look kind of like this. Let me draw this will be a table. So this could be a lab table in my room or something, and there's the floor. We could have an object. Let's let it be this. Let's make it a tennis ball, because often I have a bunch of those, and they roll off the edge of the table. So let's say this tennis ball rolls off the edge of the table with some speed or velocity, but I'm going to say this arrow here represents its speed in the horizontal direction. As soon as it leaves the edge of the table, it's going to start falling, but it doesn't just fall straight down. It's already moving horizontally, so it traces this path through space that is actually the shape of a parabola, which is the same kind of shape we see on a curved position time graph if something is speeding up or slowing down. It's the same type of shape. So this is, in dotted blue lines, we call the trajectory, which is the path through space that a projectile travels along. When we have this initial speed that's all horizontal, like this ball is rolling off horizontally, that's what makes it a horizontally launched projectile. It's not angled up and being shot at an angle. It's not being angled down and shot downward at an angle. It's going off horizontally. And these are the simplest, easiest types of projectiles to usually look at. So we have a speed in the horizontal direction. We have, I'm now highlighting in green, there's going to be this vertical distance, or you could call it a displacement. I'm just going to call it a vertical distance that the ball is going to fall downwards along, and that just goes from its initial height down to its floor height when it hits the floor. And then we also have another distance. We have a horizontal distance that goes from where it started horizontally over to where it ended. So where that blue line, that trajectory hits the ground, that's where the tennis ball is going to end up when it hits the ground. And so I can say I got a horizontal distance it traveled. So along the x-axis, how far did it travel? And then we also have in green a vertical distance, or how far it traveled in the y-axis. Its y position is changing, or its vertical position is changing as it falls, and its x or horizontal position is also changing. Okay, so all the projectiles we look at this week, any of the practice problems and the assessment question, are going to look something like this. One of the things we want to find within this sort of setup or this question, we're often going to be looking for the time t, and that's going to represent the time it takes for the ball to hit the ground, or whatever else it is. If we have a Hot Wheels car flying off the end of the table, how long does it take to hit the ground is going to be something we often want to find, which we can use our free fall equation for. So time t is going to be time it spends in the air, or how long does it take to hit the ground. Other things that we have in the notes here, kind of the shapes of what the motion graphs are for each direction. This is going to be the same for all of the horizontally launched projectiles, all of the practice problems, and the assessment question. We'll see what those look like in a bit in an example problem. The sort of math stuff that we do for the math component, we're going to be using the speed equation for the horizontal part of its motion. So it's got a horizontal speed. It's going to travel a horizontal distance. That's what I underlined in red in my picture. And it's going to take a certain amount of time, t, for it to travel that distance. We're also going to have vertically, what we can use in terms of math, vertically we can use our free fall equation, where that time t is how long it spends in the air before it hits the ground. That d is the distance vertically. So see, we have two different distances here. We have a red distance horizontally, we got a green distance vertically. So those are different values. And then little g is our acceleration due to gravity, which we'll use 10 meters per second squared for our projectile problems when you do problems. I have some info at the bottom, good procedure of what you can think about as you're trying to solve a problem, but let's do the example, the practice problem that's in there right now. Here we have a ball that rolls along a flat countertop on the table at a constant speed of 1.6 meters per second. So there's my S. And I'm going to use red for all the horizontal stuff going on and green for all the vertical stuff going on. The height of the tabletop above the floor is 0.8 meters. So that's a height above the floor. That's going to be our green distance D, because that's the vertical distance. If I drew that on my picture here, this would be the distance. I'm going to say dy, because it's in the y direction. I'm also going to color code it so it's easier to see. That's 0.8 meters is right there. How high the table is above the ground. Where the ball's coming from, that'll show the ball traveled a vertical distance of 0.8 meters. It has a speed when it leaves the table, so my tennis ball starts up here. This is just like the picture I just drew in the notes. And it leaves with a speed here. So this is going to be speed. I'm going to put an x there, speed in the x direction. You could also call this a velocity in the x direction, but that's going to be 1.60 meters per second. It's a good idea when you're doing a practice problem or an assessment when you have projectiles is to draw a little profile view sketch. So this is just like what I did before in the notes. I've got my tennis ball leaving the edge of the table. I know I have a speed or velocity horizontally. I'm going to call it speed in the x direction. And I have it in red to show you that it's part of its horizontal motion. That's 1.60 meters per second. That's how fast it's traveling when it leaves the table. It travels in a parabolic arc or parabolic trajectory, the shape it travels through space. I know this height here, this distance in green that I'm drawing, is a distance in the y direction. I drew it up and down, so let's call it in the y direction. And that is 0.8 meters. It's given in the problem. It said 0.8 meters. That's 80 centimeters, but let's keep it in meters. 0.8 meters is the vertical distance it travels. And I'm asked two questions. How long does it take for the ball? How long does it take for the ball to hit the ground? And how far away horizontally from the edge of the table does the ball land when it hits the floor? So there are two different things for me to find out. How long it takes to hit the ground, I know that's asking me to find time, t. And then how far away horizontally from the edge of the table does it land? How far away horizontally? Well, that's a distance in the x direction. Distance in the x direction. I'm going to call it d with a little x there. Both these distances, we can also describe them as displacements, but we're just going to stick with calling them distances. Speed, we're just going to call it speed in the horizontal direction instead of being too worried about velocity versus acceleration or distance versus displacement. There's one more thing I'm going to add to my little sketch here, which is going to be, here's my horizontal distance. I'm going to call it d with the little x there. Remember the x and the y, those are just there to remind me of one distance being horizontal in red, dx, and one distance being vertical in green, or dy. So dx I don't know, but I'm asked to find out how far away from the table does it land. dy I know, the speed in the x direction I know, and the time I don't know. So remember, it asks us to find the time it spends in the air and how far it travels. So time is unknown. So I need to figure both of those things out. When we start to get started, I've already done a little bit of visual work, haven't I? I drew a sketch. When I start to do my actual work for the problem, I gotta mention what principles I'm using. So I have constant velocity motion in the x, that's the horizontal direction. So that means I can use the speed equation to help me figure out the horizontal speed if I don't know that. I can use the speed equation to help me find the horizontal distance it traveled. That's the red dx, so I'm going to need to use it for that. And I also have a time t in there. So if I write my speed equation in the x direction, I have speed in the x direction equals distance in the x direction divided by time. See, I'm just putting those little x's down there to help me remember I'm talking about just the horizontal stuff. You always separate out the horizontal stuff that's happening, the vertical stuff that's happening. Separate those out and look at them separately. Okay, the other main principle that I have is uniformly accelerated motion and free fall in the vertical direction, or I can call that in the y direction. Remember, vertical and y direction are the same thing. X and horizontal direction, those are the same thing. So for that, I can use my free fall equation. My free fall equation, just like with last weekend's assessment question, you're just talking about vertical stuff, and we keep the vertical stuff separate from the horizontal. So I'm going to write my free fall equation in green, because all my vertical stuff I'm going to write in green. So I've got my free fall equation, time is equal to square root twice the distance. So here's 2 times, there's my multiplication symbol, d, and I have another distance here, a letter d, so I'm going to put the y in to remind you I'm talking about the vertical stuff. And I've also color-coded it. Now, one thing that's the same in both the horizontal and vertical stuff that's going on is the time. We're just talking about one tennis ball here rolling off the table. It's going to take one certain amount of time for it to hit the ground. At the moment it leaves the table, the moment it hits the ground, that's just one amount of time. So really this time t up here in the red equation, my speed equation, I'm going to make that a different color. I'm going to make that orange. And down here in the free fall equation, I'm going to make that orange. I'm going to say these times, time t is the same for both horizontal and vertical. So when we find the time it takes to fall vertically with our green equation, with our free fall equation, we can go and use that time for the horizontal stuff and figure out how fast it was moving or what distance it traveled horizontally. So this says same for both horizontal and vertical. Same for both horizontal and vertical. Okay. We're going to do some motion graphs for our visuals, and I did a sketch. It's good to do a little sketch like you saw me do up above. Motion graphs and sketch. I call it a sketch of the scenario, of what's physically going on. And then what else are we going to use? We got our principles, we got our equations, we got the visual stuff we're going to do. Okay. Let's look at what the visual stuff is. For our visual stuff, we can do motion graphs and our sketch. So I already did my little sketch, so I'm going to do motion graphs. We always have position, that's position versus time, PVT. Velocity versus time in the middle, VVT, and acceleration on the right, AVT. We can do motion graphs for what's happening horizontally, and we can do 3 motion graphs for what's happening vertically. That's what we're going to do. So horizontally, that's what I'm doing in red. So I'm going to say this is horizontal motion with these 3 graphs here. And notice in my picture I just happen to have a picture showing the object moving to the right. So I'm going to call to the right the positive direction here. It's good to give directions because remember when we move in linear motion, in a straight line motion, we could go this way, we could go that way. So this could be positive direction, this could be negative direction. Or this could be positive direction, and this could be negative direction. It's up to you. We're going to keep it simple, and I'm going to say to the right, that's the direction it's traveling. That's going to be the positive direction. And it's good to indicate that because sometimes we mess up, we forget what's positive or negative. Everything should just be positive for all the work we're doing this week. That's a way to make it much easier. When I label these axes, I got to label the axes. For position, it's traveling in the horizontal direction. So I'm going to say that's a position x versus time. So time t is on the x-axis, horizontal axis. I've got velocity. That's going to be the same as my speed. So you could call it v, or you could call it speed in the x direction. I'm going to leave it as both here, so you can pick however you want to talk about it. But that's what this motion graph is showing us, is its speed in the horizontal direction, which is also called its velocity in the x direction. So I can call that vx, whichever one you want. And acceleration, so that's going to be acceleration in the x or horizontal direction. and time t on the x-axis. So for all of these projectiles, we have constant velocity motion in the x direction. Look at the very first principle we put down here up at the top. If it's constant velocity motion, that means we're not speeding up or slowing down. So that means our acceleration is 0. So I can come down here and say my acceleration is 0. If it's moving at a constant speed horizontally, so as it's traveling in a curve coming down as it rolls off the table, but as it's traveling horizontally, it has the same constant horizontal speed the whole time. So this is just going to be a flat line for the velocity versus time graph, or speed in the x direction versus time graph. If we have constant speed or constant velocity, then we just have a linear, meaning we got a diagonal line either like this or like that. So I have my linear or diagonal line for position versus time. This is exactly what the motion graph should look like for the assessment question. Vertically, we can do the same thing. So I'm going to have vertical and 3 graphs that I can do. So here's 1, 2, 3. I've got to label my axes, and I'm going to say what direction is positive and what direction is negative. Like we did with our free fall stuff last week, if something's only ever moving downward, it's really helpful to just call down the positive direction, because you don't have to worry about any minus signs. So we're allowed to choose what direction is going to be positive or negative. Let's call down the positive direction, which means up is negative, down is positive. This is just going to keep everything positive, and we don't have to worry about the negative signs. When we label our graphs, which we should also title, and yes, this is all for just this one tennis ball, and we're doing 2 sets of graphs, 6 motion graphs total, because we have motion in 2 directions, horizontal and vertical. So for position, vertically, we call that y, so that's y versus time t. The velocity or the speed in the y direction, we could write that as velocity in the y direction. I put vy, or you could write it as speed in the y direction for this one. Either one is acceptable for now. Really, these are velocities, but that's okay. We can call them speeds right now. And acceleration, I have the letter A for acceleration in the y direction, and time t. So let's start with our acceleration graph again, all the way on the right. This is now talking about the vertical part of motion. So we're talking about this stuff, accelerated motion. So this object speeding down as it's falling downwards. Exactly the same as the free fall stuff from last week. If I drop something from rest, it takes a certain amount of time to hit the ground. It's accelerating, it's speeding up as it falls further and further because gravity is making it speed up. Go back and make sure you've seen that video in the notes. The guy launches something horizontally and also drops something from rest at the same time. They behave the same way in the vertical direction. They take the same amount of time to hit the ground because they have the same acceleration. And that acceleration is gravitational acceleration, little g, which is going to be our either 9.8 meters per second squared, or since we're probably going to round it to 10, I'm just going to round it to 10. And it's just flat. That's just a flat line because we have a constant value for the acceleration. In the vertical direction, it's speeding up. Remember, just like you release something from rest from your hand, it starts off at rest. So its speed or velocity in the green or vertical direction starts off down there at the origin. It's 0 to start off with, and it picks up speed at a constant rate. Every second, it gains about 10 meters per second of speed or velocity in the downward direction. So that middle graph is linear. It's the diagonal one. For the last graph, position, we start off at some 0 position, which wherever the projectile, or just imagine you're dropping something from rest, wherever it started from. And if it's speeding up, then you get a curvy graph. We saw that with the green motion carts that I had with the motion sensor a couple weeks ago when we did that. If we have something speeding up or slowing down, we have a curvy graph. So we're going to have a projectile that's speeding up in the vertical direction. So remember, vertical is all the green stuff right here. It's speeding up, so we have a curvy or squared or quadratic is another name for the position time graph. All right, we've done all our visual stuff. Let's get to figuring out our math section. So for the x direction, for horizontal direction stuff, x direction, so this is horizontal. I want to keep that separate from all of the vertical stuff I do. So I have vertical stuff over here in the y direction. Half of the kind of physics problems stuff you try to deal with is just like trying to keep everything organized. So it's good to do labels, use these little subscripts like distance in the x, dx direction, distance in the y, dy direction. So right now we're just going to list the stuff that we know and stuff that we don't know. So in the horizontal or x direction, if I go back up to my problem, I have a little sketch that helps me see what I read about in the problem. But I see that I know the speed in the x direction is 1.60 meters per second. There's something I know. I also don't know the distance in the x direction, and I don't know the time. Remember how I put the time in orange because it's the same value for both the horizontal and vertical parts of its motion. So I don't know the distance in red, I don't know the time, but I do know the speed. So when I start doing my math work, I'm just going to write down the stuff I know and don't know. Speed in the x direction is 1.60 meters per second. The time is my orange thing. I'm keeping in orange because it works for both x and y, so I'm not going to do it in red. And then I've got my distance in the x direction, which we don't know. Our equation that we care about using for the x direction, remember, horizontal direction, just using the speed equation. So it'd be like speed in the x direction equals distance in the x direction divided by time. Same equation, we're just using these little x's, subscripts they're called, to keep track of what we know in each direction so we're not getting them confused. So right here, notice we have two question marks. The things that I don't know the distance in the x direction, how far the projectile moved horizontally, I don't know that, and I don't know the time, so I can't figure anything out right now with the stuff I know in the horizontal or red direction. So if I can't figure anything out, I got to go look at some of the vertical stuff in green. Let's go look at that stuff. What things do I know from the problem? I go back up, I know I illustrated it in my sketch. I know the distance in the y direction is 0.8 meters. So I'm going to come list that down here. Okay, what's something I know? I know the distance traveled in the y direction. Let's keep it in green. Distance in the y direction is 0.8 meters. Okay. I know because this is free fall, and I'm going to be using my free fall equation, which I'll write down here. T equals, same one we used last week, same one you're using in the lab this week, 2 times, this is going to be the distance in the y direction, or vertical direction, that's why I put the y in there, divided by little g. I know the acceleration in the y direction is little g. I also have that in my motion graph, showing that I know, because it's free fall, I know what the acceleration is. So I can use this free fall equation. So I know I have little g, which I'm rounding and using 10 meters per second squared. What don't I know in this equation? I don't know t. That's unknown. So I'm going to box in blue the one thing I don't know in that free fall equation. So we got free fall equation on the right for my vertical stuff. This is exactly how you want to start your math section. Free fall equation for vertical stuff, vertical part of its motion. Over here on the left side, I have the speed equation for horizontal stuff, or horizontal part of its motion. And that's all we need. Now we're basically looking at motion that has both directions happening at the same time. So notice I can't use my speed equation yet because I have 2 unknowns in there. I don't know the distance in the x direction. I don't know the time t. I'm stuck. Can't do anything. So I go and look at the vertical section, the vertical side, over there on the right. I notice the only thing I don't know is that time t. That's the only thing boxed in blue. I know the other stuff. I know what dy is, the distance vertically that it travels, 0.8 meters, and I know little g. So let's do that one. I'm going to find out what the time is. So I have twice that vertical distance is 0.8 meters, so I got 0.8 meters upstairs divided by little g is 10 meters per second squared. Exactly the same as what we were doing for the free fall stuff last week. 2 times 8 is 0.8 is 1.6 divided by 10 meters per second squared. So we have a time that is equal to square root 1.6 divided by 10. That's 0.16. My units are seconds squared until I take the square root. So you can use a calculator at this point if you want, or just recognize that it's a perfect square and get your answer. But remember, if you're typing in your calculator, make sure you do the square root part and get the full value at the end, which is going to be 0.4 seconds. So now I have the time. That's how long it takes if I shoot a projectile horizontally from a 0.8 meter height above the ground. It's going to take 0.4 seconds for it to hit the ground. The exact same thing happens if I drop an object from 0.8 meters above the ground, or 80 centimeters, same thing. If I just drop an object from rest, it's going to take 0.4 seconds to get to the ground. Exact same thing. Remember that video at the beginning of motion notes number 3, they both take the same amount of time to hit the ground, whether you launch it horizontally or just drop it. So we've gotten our time. Look what we can do now with this time t, which I had kept as orange because I was going to say it goes in both horizontal and vertical have the same time because it's just one object. So it's the same time for both sides, horizontal and vertical. So I can take this time that I found and I can go substitute it in over here in that speed equation. So now we know our time. We just figured out what it is. I can even add that to my little list of things that I know. I now know the time is 0.4 seconds. I'll do it over here for the vertical section. I now know the time is 0.4 seconds. So that was one of the things being asked for in the question. How long does it spend in the air? How long does this horizontal projectile, this tennis ball, spend in the air before it hits the ground? And then also we were asked to figure out how far away from the table does it land? What is its horizontal distance traveled? That's the dx. So now we just need to figure out what this dx is right there in that speed equation. Remember, you always want to isolate or get that variable by itself before you start plugging stuff in. So all I got to do to get it by itself, I'm going to rewrite this equation right here. All we have to do to get it by itself is I got to get rid of that t. So I'll show it in pink. I'll multiply both sides by t. Whatever I do to one side, I have to do to the other. Otherwise, the equation does not stay true. I'll show in green here, canceling out my time t. That's why I multiplied by it on both sides. So I have, in my next line down, time t multiplied by this speed in the x direction is equal to the distance traveled in the x direction. Notice I keep the x's there to remind myself I'm using the horizontal stuff, because I also have a dy for the vertical distance. That's not what I want to substitute in here. I want to use the horizontal one. Horizontal stuff when I'm on the left side over here in my horizontal direction. Okay, so our time was 0.4 seconds. Notice I'm keeping the units in there to make sure they all agree. The speed, I look back up, look at my little table of stuff that I know, so I don't have to go read the problem again. 1.6 meters per second, or 1.60, same number, equals the distance it travels in the x direction. So now, again, we got some easy numbers here, but you take out the calculator if you're not sure. 0.4 times 1.6. And I've got some a distance that we travel horizontally, 0.64. 0.64 meters. Look at our units here, because I wrote them in. I got seconds. That would be in the numerator, seconds over 1, canceling with our seconds in the denominator. So I'm just left with meters. That's good. That's a unit you want for distance, meters or centimeters. Okay, so that's the distance in the x direction. This is something about the horizontal stuff that we're solving for. And there we have answered both parts of the question we were asked to solve for. How long does the object spend in the air? How long does it take to hit the ground? And also, what horizontal distance does it travel? We'll have a few other practice problems up there for you to look at, where maybe you're given different things. Maybe you're given the horizontal distance it travels and the vertical distance, and you got to figure out what the speed in the x direction is. Well, it's the same sort of stuff. You'd have the same motion graph, same baseline principles. But when you go to do your mathematical work in the math section, maybe I give you dx is something you know at the beginning, but you don't know the speed in the x direction. You don't know the speed in the x direction, so you have to go and solve for that. Same equation that you would be using. We're always using the speed equation here in the horizontal or x direction, and we're always using our free fall equation over here in the y or vertical direction. So we've taken the first week of motion, looking at the speed equation and constant velocity motion in the horizontal direction, and now we've combined it with motion in the vertical direction, which we can analyze mathematically with this free fall equation. We can put them both together to figure out stuff about a projectile, a type of object that moves in both the horizontal, or x, and the vertical, or y, directions at the same time. It's the only type of projectile we'll be looking at, and this is a great outline for how you should approach all the practice problems and the assessment question for this week. Remember, in the qualitative part, which we'll go through just briefly, when you're explaining what you did, complete sentences, I want to touch on each thing. So in the baseline, the fundamental stuff, principles, I can say I'm applying constant velocity motion in the x or in the horizontal direction, and uniformly accelerated motion and free fall in the y direction. All right, so I'm stating right there, constant velocity motion in the x direction. That's true with our projectiles because we don't have air resistance that it's got to push through. We don't have a rocket attached to the back of the tennis ball. That would change, perhaps give it some acceleration in the x direction. We don't have that. A projectile, it just has constant velocity motion, constant speed in the horizontal direction. So I state that in my qualitative explanation. UAM, accelerated motion, and free fall in the y direction. That immediately tells me stuff that I know. So I can say I know speed is constant in the x direction, or acceleration in the x direction is 0. I know speed is constant in the x direction as a result of that principle. And acceleration due to gravity, that's our little g, or you could just write little g here, acts in the y direction. I've given a good statement about what fundamental principles are guiding me in trying to solve this problem. My visuals come next. I want to point out something about my visuals. So I did motion graphs for the horizontal and vertical motion separately. That's what's in red and green. So I made motion graphs. You need to include motion graphs in your assessment question for visuals. I made motion graphs in the horizontal or x direction and in the y or vertical direction. And I did a little sketch and did a sketch of the physical scenario, a sketch of the physical scenario. So notice that was up there. That helped me kind of map out the things that I know about the physical scenario. It's just a little sketch, and I'm using those brackets or those lengths in red and green to show what I know, what value, 0.8 meters. Is that vertically or horizontally? When I do a little sketch and label it, that helps me keep track of it. Okay, last thing we would talk about is our math part. So I used I eventually used the speed equation, but first I had to use the free fall equation. I used the free fall equation to find time the ball spent in the air, and the speed equation, to find the, what did we solve for? We figured out the time. We knew the speed of the ball in the x direction already, so we used the speed equation to then find the distance traveled in the horizontal direction. So to find the distance traveled in horizontal direction, which was, and here's where I would write dx to connect it directly to the symbol I was using in my math, was 0.64 meters. And I was also asked to find the time, so I'm probably going to say, and the time t was 0.4 seconds. All done. So I got a qualitative statement, a few sentences that describe something about the baseline, what I was using, something about the visuals, what I was using, something about the math that I did. No new equations. We're just using speed equation for what's happening horizontally, and we got to kind of bracket the horizontal stuff off separate from what's happening vertically with our projectile. And then the same equation we used last week, free fall equation, for figuring out the time it takes for it to hit the ground over there on the right side. All right, that's it for our first projectiles video. This will cover any of the practice problems or the assessment question this week about how to approach it and what kind of stuff we're doing with projectiles.